Okay, so welcome to this next video in which we are discussing field extensions. Okay, right, so in the previous video we saw the archetypal example of a field, which is the rational numbers, and we saw that it does not contain solutions to this polynomial x squared minus 2x minus 1 is equal to 0. So, in this field that we've got here, there are no solutions to that equation. Now, the idea of a field extension is that you can make a bigger field, which then will have solutions to this equation. Okay, so, the rationals then is a set, okay? So it has all of the fractions in equivalence classes, of course, because there are many equivalent fractions that are all grouped together as a single element, basically. But it has a huge number of elements, okay, and it has an addition and a multiplication law defined on it. However, it has no solution to this equation x squared minus 2x minus 1 is equal to 0. So the idea is, how about we add in extra elements? How about we put on some more elements, make the structure bigger, keep all of these original ones here, but add on more, basically, and then end up with a bigger field, a new field, which is a field extension, although, as we'll see, this is the crude conceptual view of a field extension. A field extension's rigorous definition, the proper rigorous definition, is more subtle than this. But this is the intuitive the intuitive interpretation of what a field extension is. People will often refer to the field extension as this bigger field which has the initial field sat within it, basically. Okay, right, so if we add on these extra symbols, we're then going to have to also extend the Cayley tables. So if these were the original Cayley tables, here's the addition, and you have, for every rational, you have what every rational added to every other rational is, and then you also have the Cayley table for multiplication over here. So you have what every rational multiplied by every other rational is. You're then going to have to add on the new elements that you've put in. Okay, so you've added this whole bunch of new elements, so they're going to have to be added on to both Cayley tables, basically. So here's the original Cayley table for multiplication, but you're going to have to extend it, and you're going to have to define all of these new entries here. Okay, so this concept of building a bigger field which contains your old field, this is the concept of a field extension. At least this is the intuitive concept that we're going to use most of the time, okay? So usually when people talk about field extensions, they talk about, well, what they mean when they say a field extension of the rational numbers is this bigger field which contains the smaller field, okay? As we'll see it right at the end, there is a more rigorous definition of what a field extension is, and it isn't actually the name for the bigger field. Instead, it's the name for the function which maps the smaller field onto the bigger field, the monomorphism, as it's called. Sorry, meromorphism, not the monomorphism. Okay, but we'll talk about that later. Okay, right. So let's think about this, because we're going back now to our motivation for defining this bigger field. Okay, great, we can define bigger fields potentially that contain the rational numbers, but why? What's the point? Well, the point is that there may well be solutions of this polynomial equation in the bigger field, and because the bigger field contains all of the elements of the rationals, of course the polynomial still makes sense in this field extension, because all of the elements that are referred to in the polynomial, such as 2, well, the additive inverse of 2 and the additive inverse of 1, they're all still present, basically, in this larger field extension, so the polynomial still makes sense in the context of this field extension. Now, an example of a field extension for the rational numbers would be the real numbers. Okay, so the rational numbers is a field, and it's contained within a bigger field, which is the real numbers. So all the rational numbers are within the field of real numbers, but the real numbers is much, much bigger. Okay, and in the real numbers, there are solutions to this equation. Okay, so let's discuss them now. So, the equation that we were discussing was x squared minus 2x minus 1 is equal to 0. And we said that any solution to this equation would also satisfy the equation x minus 1 squared was equal to 2. So, we then need to look for real numbers which square to give 2, and then all we need to do is say which real numbers subtracted by 1 equal those real numbers which can square to give 2. Now there are two real numbers which can square to give 2. One is the positive square root of 2, and the other is the negative square root of 2. Okay, now both of these numbers will square to give 2. So one option for x is that it's the real number which, if you subtract 1 from it, is going to give you the positive square root of 2, and therefore x is equal to 1 plus the square root of 2. The other option for x minus 1 is that it's equal to negative the square root of 2, and therefore x is the number which, if you subtract 1 from it, gives negative the square root of 2, and that implies that x is equal to 1 minus the square root of 2. So these are the two solutions then to your equation in the real numbers. Okay, so we have found a bigger field which then has solutions to the polynomial equation in. Okay, so this is a field extension of the rational numbers that now contains solutions to this equation. However, it feels a little unnecessary. Okay, we have gone from a countable set, the rationals is a countable set, okay, to an uncountably infinite set, which is the real numbers. Okay, so this is a massive jump, and it feels as though there should be a more efficient way of doing this, and indeed there is a more efficient way of doing this. So basically there is a smaller field extension that you can make. So let me define a new field. Let me define the field which I'll call K, which contains all symbols of this form. So initially I'm just going to define it as a whole new field, then we'll see how you can think of the rationals as being contained within it, and then we'll use this to see the rigorous definition for a field extension. Okay, right. So this whole new field I'm going to define is firstly a set of symbols. Okay, so I'm going to define a set of symbols. I'm going to define all things of this form, where A and B are rationals. Okay, so basically, you are going to take A, which is a rational, and for each A, you're going to vary B over every possible rational that exists, and then you're going to also vary A over every possible rational that exists. So you could draw out a great big table for this. Okay, so you'd put in every single rational along here. Okay, so maybe you'd have in 1, a half, maybe a third, just to give a few examples. And let's say this is the A portion here, and you'd also have these rationals all stacked along here as well. Okay, and then what you'd do is this would be the B portion, and then you'd put them together. So here is A, so this is 1 plus 1 times the square root of 2, and then you'd continue on constructing it. So the next one along would be a half in the A position plus 1 times the square root of 2, and you'd go on and on and on. The next one would then be a third plus 1 over the 1 times the square root of 2. Okay, so you create all of these new symbols, and I'm just viewing these things as symbols. Why not? They're just squiggles on a piece of paper. So each one is just a placeholder, basically. It's just a symbol at the moment. That's all I'm defining it as. Of course, it's highly suggestive the way I've done this and put an addition here, but you could just view it as symbols, basically. These as being symbols. Okay, and when we see the rigorous definition of a field extension, it's more helpful to think of these as just being symbols. Okay, right, so I want this to be a field, so I need to define an addition law and a multiplication law on it. So, basically my addition law, let's define addition here. Okay, so I'm going to define an addition law on this set now. So, if you take an element, which is, let's say, a plus b square root of 2, and you want to add it to another element of this set of symbols, which, let's say, is c plus d the square root of 2, then I'm going to define that to be equal to a plus c, where this is addition in the set of rationals, basically, because this is addition in my new set, this is addition in the set of rationals, and then we're creating a new symbol, so this is just the plus in the symbol here, basically. So if you want to decide what symbol is going to be in the first position, you add these two symbols, a and c, in the rational numbers, okay? So you add them in the field of rational numbers, and then this is just the plus that's in the symbol, basically, and then the rational number that's in front of the second portion is just going to be b plus d, basically. And again, that will be addition within the rational numbers. And then it will just be multiplied by the square root of 2. Then we'll define multiplication similarly. Okay, so we're going to define multiplication of these two. Okay, so we'll define a plus b times the square root of 2 multiplied by c plus d times the square root of 2. And we'll define this to be, basically, we'll do it in the intuitive way that we know how to do it, but in principle you could view this as just a definition. Okay, we'll take a times c, okay, and we'll add that to these two multiplied together, which is plus 2bd here. Okay, and then we'll add this. That will be the symbol that's in the first position, and the symbol in the second position will be AD. So this one multiplied by this one, plus BC times the square root of 2. Okay, so that's our multiplication law. Right, so we need to prove that this is going to form a field under addition and multiplication, and we also need to understand how this contains our old field and how also it's going to contain the solutions to this polynomial equation, x squared minus 2x minus 1. Okay, and we'll use this to understand the more rigorous definition of a field extension. So firstly, let's just prove that this is going to form a field. Okay, so firstly, addition. Okay, so we firstly need to prove that it has an additive identity. Okay, so the additive identity, therefore, is going to be the element where you have 0 in both positions. So A is going to be 0 and B is going to be 0. So it's going to be the element 0 plus 0, the square root of 2. And the reason is that if you add this to any other element, let's say A plus B, the square root of 2, where A and B can be any rational, then just using our own rule here, this is going to be 0 plus A plus 0 plus B times the square root of 2. Okay, and if we're adding these two in the rational numbers, of course, 0 plus A and 0 plus B is just going to give A and B respectively, so this is going to take us back to A plus B, the square root of 2. So this symbol here, added to this symbol, is just going to give this symbol back again. And that's going to be the same if we do it the other way around as well, because of commutativity of addition in the rational numbers, and also because, of course, 0 is the additive identity in the rational numbers. Okay, so we do have an additive identity in our new field. Okay, now let's check additive associativity. Okay, so we want to check that if we have A plus B, the square root of 2, and we're going to add that to another symbol, C plus D, the square root of 2. Okay, and then we'll take the answer to that and add it to another symbol, E plus F, the square root of 2. We want to check that that's the same as if you take A plus B, the square root of 2, and then add it to the answer of C plus D, the square root of 2, plus E plus F, the square root of 2. Like so. Okay, right. Well, we're just going to plug in the definition here. Okay, so a plus b the square root of 2 plus c plus d the square root of 2 is just going to give us a plus c plus b plus d the square root of 2. So that's the answer here. Now we're going to add this onto this. That's going to give us overall a plus c plus e in position 1 plus b plus d plus f in position 2 times the square root of 2. Now what we're going to do is apply associativity to associativity of addition in the rational numbers to say that this is the same as if you have a plus c plus e, okay, plus b plus d plus f, like so, times the square root of 2. So that's associativity of addition in the rational numbers, because remember the way that we get the rational number that we have in position 1 and position 2 is by adding these rational numbers in the field of rational numbers. Okay, right. And then we can start to break this down. We can break this then down into the symbol a plus b the square root of 2 added on to, at the moment we've got the symbol which is c plus e plus d plus f the square root of 2, but then we can break that down further into these two added together, and therefore we get that yes indeed this side is equal to this side, so we do get additive associativity. Thirdly, we want to show that there are additive inverses. So we want to show that if we take an element a plus b the square root of 2, there exists another element that we can add to it to give the additive identity, which is 0 plus 0 the square root of 2. But that's simply going to be negative a plus negative b the square root of 2. So just stick in the first and second position the additive inverses of both of these rational numbers in the rational numbers, and then when we add this to this in our new field, then what it's going to be is a plus negative a for position 1 plus b plus negative b for position 2 times the square root of 2. But of course both of these are just going to equal 0, so this will be 0 plus 0 times the square root of 2. Okay, so we get that additive inverses exist. Okay, right. So, next property is commutativity. Okay, so we want commutativity. Right, and this means that we need a plus b the square root of 2, so a symbol within our new field, plus c plus d the square root of 2, another symbol within our new field. We need this to be the same as c plus d the square root of 2 plus a plus b the square root of 2. Now this is going to hold simply because we have commutativity of addition in our rational numbers. Okay, so if we use the definition of how to add these two symbols together, we say that in position 1 we'll have a plus c, where we're adding them in the rationals, and then plus, which remember is just a symbol here, b plus d, again added in the rationals, times the square root of 2. And on this side it will just be c plus a plus d plus b the square root of 2. Okay, but of course b plus d is the same as d plus b, and a plus c is the same as c plus a, so these two symbols are the same. So that's how we get commutativity of addition in our new field. Now let's turn to multiplication. So we need a multiplicative identity. Okay, so our multiplicative identity is just going to be the symbol 1 plus 0 the square root of 2. And the reason being that if we multiply this by any other symbol in our field, so let's say we multiply it by c plus d the square root of 2, the answer is going to be c. So we take this one, multiply it by this one to get c. We multiply this one by this one to get 0, of course. Well, actually, let's go back to our definition of multiplication. So I'll write out the definition of multiplication. So if we've got a plus b the square root of 2, and we're multiplying it to c plus d the square root of 2, the answer is that this is ac plus 2bd plus ad plus bc times the square root of 2. Okay, so in position 1, we want A times C, but that's just C. Then we want 2 times BD, but B is 0, so 2 times BD is going to end up being 0, so that's just going to end up being C. And then in position 2, we want A times D, which is just going to be D, and then we want plus BC, which is going to end up being 0, so this is going to end up being C plus D, the square root of 2. Okay, and that's also going to work on the other side as well. If you do it on the other side, it will give the same answer. Okay, right. We will continue our discussion of this in the next video.